Finally, there's this observation, which I think is quite important. I think that the vacuum in the sitter space is not empty. Well, first of all, there's dark energy, but there's also entropy sitting there. And the analogy you should have is with a crystal or glass, because the crystal does not really have entropy. It has a unique ground state. It has unique configuration, but a glass has very similar properties. But the difference is that it has lots of entropy in it. That's a pity. That's only 5 minutes, because I had something to say about the other stuff. Anyway, maybe I should. Yeah, actually. Actually, maybe I should. Well, I don't know. Yeah, anyway, what I wanted to do continue is actually this idea of that indeed there is an entropy in the state, and that actually does affect the gravitational laws. And I actually made a model actually very similar to this polymer idea. I sometimes show this, that you have this silly putty that when you measure it at short time scales, it's bouncing, it has elasticity, but at long time scales, it actually flows very much like a glass. And the physics of it actually was solved by De Gennes using equations that I could use actually. And actually there's an equation that I want to show here. Actually has some models with these polymers. And it's this equation that eventually played a role. So I'm claiming the fact that there is an entropy in our universe actually causes an additional force that is due to the dark energy, and it behaves sort of like an elastic force. And the thing that made me sort of believe this is the following fact, that there is a very nice way that elasticity and gravity can be mapped onto each other, precisely using an acceleration scale. All of the quantities that we know from gravity are related to associated quantities in elasticity by simply putting in one scale. Then you can take the equation that was derived here and rewrite it in some other form, namely using these equations. And out comes an equation, which I put here. Actually, I have to assume a certain volume here, which is sort of has to be put in. But anyway, this equation can be derived using the same math that we can use on polymers. And it actually is an equation that explains this behavior. Basically, it gives you a Mondt-like scaling, or what's nowadays called this radial acceleration relation. And the equations indeed can be tested, and this is precisely what Margot has been doing, by not just comparing with rotation curves, but also with weak lensing data. And this is what actually is important here, is that you're not just testing it in very short distances with slow with a certain acceleration, small but not so small. You can even go further, and in longer distances, even weaker acceleration, and you still have this same relation extended over these many decades. I want to finish actually with this other part, which I'm going to be brief about. Actually, we heard a talk by Nikki this morning about the Hubble tension. And actually, maybe this is where I want to get to. Because one thing that you can actually get is from this whole idea of emergent gravity, something that I call an effective dark matter density. So the equation that I showed you can be rewritten in a form where the dark matter density is related to the baryonic matter and the full critical density. And it depends also on the scale that you look at this, because this you can indeed put also in scales of clusters and so on, or galaxies. But you can also take R to be the radius of the universe. And in that case, you actually get a prediction for the dark matter abundance. And actually this formula comes out, which is something I put here. And this is sort of where it would lie with the data. So it's something that agrees with C and B values very well. But now I want to get indeed to the final thing, which is sort of this cosmological evolution. And here I just want to show a little bit the plots and the model that I put in. But there's a disclaimer. I mean, I think if we really want to discuss this very seriously, I should develop the theory of emergent gravity much further. We should have some way of deriving dynamics and having some analog of the Friedmann equation, or something that at least we can derive from this microscopic picture. What I've done here is a very simple thing. I basically took my phenomenological relation and put it in the Friedman equation and see simply what is the consequence. Why I'm interested in this, of course, I want to see if maybe this idea might help us understanding something about the tensions that we are being observed. Because it's another model on lambda CDM. It's not a model that would change dark energy, like was explained this morning. It would be a different equation of state or a different evolution of the dark matter component. So that's the basic idea. So I want to briefly show you what is the outcome. So this is the Friedman equation with all of the components in there. Now, normally we start playing a little bit with this, but we always assume that dark matter is doing what it's usually doing. In our model, we do something different. Namely, we say that all of these terms are there, but I'm going to think about the dark matter as this effective dark matter component that has a relationship between the full matter. And matter actually, for me, matter is anything that's a particle. It also includes radiation. So there is a way that I'm going to write this equation, and so that the relationship actually is between the dark matter density and this combination of the baryonic and radiation density. So I'm going to put this in this equation and then see what the evolution is doing. And you find some plots that indeed the dark matter actually in the radiation dominated area actually becomes, well, growing actually. But then there's something nowadays that we can fit quite well with what is being observed. But in the intermediate time, actually, it turns out that the dark matter density is much smaller than what we would get from lambda CDM. But you can ask, is this in agreement or in disagreement with observations? Because the observations are generally only, actually, there's something not showing on the slide. I had a gray band here. Do you see something gray here? Because I see it on the slide here. Anyway, there's some here because the redshift 1000 has sort of been selected here because that's something where we should verify the CMB. So the fact that we get something of the order of 1 there is quite important because that makes this consistent with CMB data. Same is true for Hubble. I mean, we find, of course, I try to play in such a way. I mean, I don't think I fitted that many parameters. There, of course, there's a bit of a thing involved to get at least the same data that we have at short and long distances, but it's possible to have a higher H0 now and something in the radiation or whatever in the CMB area where we get a reasonable fit with the CMB. So these are things I would like to indeed test also as well. And exactly what was explained this morning, I also verified that things like the sound horizon and the angle that we see there basically works out, and I use the standard equations for those. And this is where I want to just end to show you a little bit of those plots. So this is the co-moving distance evolution. So this is what I basically, how I define it. So there's an h of z, you integrate it, and then you can see what that does in these two models. So I'm comparing lambda CDM to the model that I have. You see some deviation, actually quite a high one here. And there's also things like the sound horizon that's doing things like that. But the actual variable I'm interested in is this angle, because this angle is the one that we want to compare to the observations. And again, there should be a gray band here, which tells you that, well, the CMB is being decoupled around here. And that's indeed where we find that our model has at least agreement with what is being observed and also what would be following from lambda CDM. So I want to stop here because this is, well, as I said, some bit of a speculation because I didn't fully develop the entire theory yet. Okay, thank you.
Thank you. Are there any questions? I see one on the front row, or well,
yeah, Erik, could you put on your third or fourth slide where you showed the polymer being heated up, and then you talked about, well, my question is about the difference between the relationship between gravity on one side and entropy and the change in entropy. It seems to me that there are two different things, and your polymer example was a really good example of how a change in entropy, delta S, has a force, but the S, you can only make that force when you have a delta S going on. But once that polymer the entropy is no longer changing, then there's no longer a force. It's kind of like the Gibbs free energy has an entropy in it, and that describes the thermal equilibrium, but it's not a force. You have to be changing the entropy in order to extract a force from that equation. So that's my confusion.
I spent some time explaining that confusion here. The actual equation here is that when you lower the speed, you're doing it adiabatically. Because if there would not have been the force, the entropy would have changed. So the force is actually making sure that the entropy does not change, but the consequence of the force is the tendency to change the entropy. So this is a reversible system. So when you're lowering it, you're actually extracting heat from the heat bath.
Yes, yes.
And that amount is the same as the amount of entropy that's increased in the polymer configuration, because the polymer configuration contains more entropy when it's short, but the heat bath will take it out. And that is actually the work that you can do.
Well,
with
that part
this
I
system.
understand. That part I understand. I don't understand what it has to do with entropy itself. This is the change in entropy. Why would there be a force associated with entropy?
Oh, sorry. It's indeed, if the entropy itself would not be a force, it's if there would be an effect that changes it,
yes,
then there would be a force.
Yes.
But it means that you're moving things around, I mean, from one side to the other. But you're right. But that's the same is true for gravity.
Well, but the rest of your talk talks about not delta S dSdt, but rather S and gravity, not dSdt.
No. I have always the equations here where there is a D here acting. That is actually the change. Okay. So if you want to derive Einstein's equations, you have to take the effect of the change in the curvature, of change in the area when you add matter. So this is what actually one way to think about GR, by the way, is indeed if a mass is there. Why is there curvature? Actually, if you take the mass of a volume of space, so the area of a certain volume of space, that area changes when you put a mass inside. And that's one way to think about curvature.
Okay, if you have time, we'll just do one more question.
Right, thanks. That's really fascinating to learn. And towards the end, Erik, you showed the expected expansion history of the universe predicted from this theory, and also the matter ratio. And it seems like between the CMB and the current stage, they are roughly about the same as we would expect, but in between, there's a fairly dramatic difference.
That's correct.
And I wonder if you would expect a rather different integrated Saxon-Wolf effect through those drastic changes.
Well, these are exactly the kind of things. So the question is, what are our observations that constrain the time evolution between those? And you have to, of course, understand for which redshifts this is relevant. And I think I have it in the plot. Maybe I should show you, but then I have to go through all these slides again. Let me maybe do this quickly. No, I mean, the baryonic acoustic oscillations, as we heard this morning, is also important constraints, which I haven't fully digested yet, but there are consequences. So this is, I think, the one you mean or yeah. This one here. And there are consequences here, of course. I mean, one thing that I find at least assuring, I mean, is that I think this also tells you that there should be less structure formed in the time because of so the sigma 8 might actually be consistent with this, but there are all kinds of effects that might have, well, be associated with it. But of course, there are other things in this model as well. There's still dark energy and there's still the ordinary matter that you have to take into account anyway, but this is just the dark matter component. And as you see here, the redshift is already 10. It's not something that is immediately measured. I mean, there's this region might be interesting to check. So this is why I'm quite interested in how they can see the equation of state of changing or the evolution of the universe at redshifts of 2 or 3, because then you can see these turnarounds quite well, maybe better.
Okay, thank you. Erik will probably also be available for questions during the lunch, so we should thank him.